Okay, so in this part of the course, we're going to talk about DC circuit analysis. And we're going to use some of the standard tricks to solve some DC circuits. But to hammer home the point, we've built one here. It's fairly simple. It just has 3 resistors. They're all equally valued at, it looks like, 2 kilo ohms. Now in these leads, we can put in batteries or voltage sources. So let's actually sketch out what we have here. We have a 2 kilo ohm resistor. We have a battery, which will be, say, 9 volts. That's going to go to this green thing here. To that green wire, we're also going to put another battery, a 6-volt battery. And on the other side, we have this 2K resistor here. And finally, we have a third 2 kilo ohm resistor here. So before we actually do the math and calculate, let's actually just measure it and see what we get. So we're going to go here. Okay, and here's our circuit that we were just looking at here. First thing we got to do is give it some batteries, and let's draw it out again for a little bit of clarity. So we had our 2 kilo ohm resistor, we had a battery, we had another battery pointing the other way, and we had a 2K. And to wrap it up, we also had a 2 kilo ohm resistor in the middle here. So let's set these up. So we're going to want, I think we had a 9-volt battery. Set them close. Make sure these things aren't shorting against one another. We'll get out our handy multimeter. And probably turning it on helps. 8.11, that's almost there. So let's crank it up to 9 volts. Oh, it's just about there. It's about as close as we're going to get it. And we want 9 volts. Here's our negative side going here. So we have a 9 volt battery across there. And on the other side, we wanted 6 volts. And let's crank it up to 6 volts. Yeah, it's pretty close. Okay, good. So the positive side was going to this positive side of the other one. We got a nice floating supply here, so we can do this. And the negative went to the negative side, and that's what we got. We had our 6-volt battery here. And now we can start measuring some things. So the first thing we might want to check is the voltages across here. So let's look at the voltage drop from here to here. We'll call this node A to B. And we can do that directly with the multimeter. The voltage drop from here to here, well, that's the same anywhere along this line. So let's poke it right there and here. And it looks like we got just about 5 volts. So delta V, so I'll say V A to B is 5 volts. Meaning this is 5 volts higher here than it is here. Let's call this point C. And this is also B. So let's see what the voltage drop here is. Again, we'll start at C. And what do we get? -1 volts. That makes sense, I think. We lose 1 volt. We've lost 5 volts from here. And that means this point is 5 volts higher than this point. -1 volts means this point B is 1 volt higher than C. We've gone from here, we lost 5 volts, and we lose 1 more volt this way. I'll put a little arrow here. And really, to be clear, this is voltage from from C to B. An equivalent way of writing that is VCB from here to here. Sorry, an equivalent way of writing this is VBC is equal to +1 volt. From here to here is a volt. Okay, last one, last voltage that is. We'll measure from D, we'll call this point D. From D to B, this is all one point. They're all connected through this blue rail here. So we'll start at D again. Up here or here, anywhere along this equipotential, this wire, to the bottom, and I probably better put the multimeter on screen here. We're going to get negative 4 volts. So we got negative 1 volt here, negative 4 volts, and we had plus 5 on this one. Great. So VD to B was minus 4 volts, or VBD was equal to 4 volts. Same thing. Okay. There's a few more things we can measure. We can measure the current along a few of these places. Remember, when we're doing current measurements, it's a bit trickier. We have to make our multimeter part of the circuit. We actually have to make this current flow through our meter here. Current's going to flow through a small shunt resistor there. So we're going to set up the current. I'm going to be very careful not to measure in parallel, because then I just have a very small shunt resistor in parallel in this meter, and I will blow a fuse. Now, when we're measuring the current, we have to be careful to put the multimeter in the right setting, in milliamps, and be careful about how we do it, because as we do that, what actually is going on inside this multimeter is we actually have to draw current through the multimeter. Positive current means in through the red, out through the black. If it's negative, that just means it's flowing in through the black, out through the red. But the important thing is how it's doing that. It's drawing current through a very small shunt resistance here. So I won't actually do it, but if I put in parallel here, if I'm trying to measure the current across this resistor and I do it by accident in parallel, I've just bypassed that resistor and put a fixed voltage across a very small resistance here, and I've blown a fuse. So in order to measure current, we measure it in series. We disconnect a wire and we make our multimeter part of the circuit. So let's measure the current downwards through this path here and see what we measure. 0.5 milliamps. So we got 0.5 milliamps. What we actually measured was negative 0.5 milliamps here, but that's equal to plus 0.5 milliamps going upwards, right? Half a milliamp down is negative half a milliamp down is plus half a milliamp up. So let's reconnect that, and we'll measure the current in the middle. Okay, so we measure the current down through the circuit. If it's positive, we guessed in the right direction. If not, it's in the other. And we get 2.48, pretty darn close to 2.5, if you can read that chicken scratch. So we'll start filling in this node A here, so we can do some bookkeeping. We had 0.5 milliamps, 2.5 milliamps. See if we can guess what we should have here. Well, if we have 2.5 milliamps flowing this way, we have half a milliamp flowing this way, it looks like we better get 2 milliamps flowing into this node. We'll disconnect as we had before, measure the current going downwards through there, and we get, drum roll, negative 1.99 milliamps. Negative 2 milliamps this way, which we just learned is the same as 2 milliamps going up. So indeed, we get 2 milliamps in here. Okay, so this is one way to solve for a circuit. You can just build the circuit and measure. It's not always the most efficient way. It can be a very complicated circuit, or you might want to play around with it a bit. Or maybe you want to calculate what you're supposed to get before you build it and spend a lot of money. So luckily, there's a lot of other ways to solve for a circuit. We can use Kirchhoff's law, which will be in the next video. We can use superposition, which will be in the video after that. Or we can use the idea of Thevenin equivalent circuits, and we'll do that in the final video.